Just check. Good afternoon, everyone. My name is Lucian Pullen, and I will be your tutor for today's Yabble Physics session. Okay, now today we are doing linear momentum and collisions, and well, this week we are doing linear momentum and collisions and the rotation about a fixed axis. But today specifically, we will mostly be focusing on momentum and collision, linear momentum and collision. Now, just change my color to my pen, back to black. Okay, so let's not waste any time and do a quick recap. What is momentum? Okay, momentum denoted P is equal to mass times volume, correct? Now, since volume is a vector, momentum is a vector as well, with mass being a scalar. Now, what is the change in momentum? Now, the change in momentum is equal to the momentum at the beginning, or the momentum at the end minus the momentum at the beginning. That's how you get the change in something. Okay, but we can also write this as mass times velocity at the end minus the mass times velocity at the beginning. Now, mass in most times, or usually it is a constant, so we can take it out. Most of the time it is a constant, so we can write it like this. So it'll just be the change in the velocities. But mass won't always be a constant, so this won't always apply. It will not, this formula will not always be valid. An example would be in the case of rocket trajectories or rocket ships. As the rocket ship is go moving upwards, it is burning fuel, meaning it gets lighter, so its mass is changing. So in that case, this formula will not work, so I would rather stick to the one above. But the change in momentum also has another name, impulse, which is denoted by an I. Okay, and that is basically all we need to understand momentum, linear momentum and collisions. It's these formulas. Okay. Oh yeah, you can also write impulse can also be written as I is equal to force times the change in time. Okay. You can also write impulse in that manner. Just a fun fact, Newton wrote his Principia Mathematica, his laws of motion, in terms of momentum. Okay, so let's start with the first problem. It says, after a zero point 0.3 kilogram rubber ball is dropped from a height of 1.7 meters, it bounces off a concrete floor and rebounds to a height of 1.5 meters. So momentum was lost, okay, because it did not bounce to the 1.75 meters. It started from, it bounced to 1.5. I mean to the 1.75 meters it started from. It just bounced to 1.5. Okay, meaning there was a change in the momentum. Okay, that is what we know straight off the bat. Now they ask us, determine the magnitude and the direction of the impulse. So number one, the question, number 1A, determine the magnitude and the direction of the impulse. Now remember here, we are only working in one direction, that is in the y direction. So let's call it in the j hat direction. Okay, so we're working in the j hat direction. So we know that our momentum will be in the j hat direction. Now, before we start answering here, let's just look at quickly at something. Uh, we are choosing, in this case, we are choosing upwards. Let me just see here. I want to switch screens quickly. I'm choosing upwards as positive and downwards as negative. Okay, upwards as positive and downwards as negative. That is my convention. So all my vectors pointing upwards will be negative, and those that are downwards will be negative, of course. All my vectors going up is positive, and my vectors going down will be denoted with a negative. Okay, that is just my sign convention. I always choose up as positive. You can choose it That's negative, won't change the final answer. Okay, depends on what you chose. Okay, now they ask us, A, determine the magnitude and direction of the impulse delivered to the floor. But what is impulse? Impulse is nothing but the change in the momentum. Okay, the change in the momentum. And how do we get the change in the momentum? Mass times velocity final minus mass times velocity initial. In this case, the mass will be constant, so it's just velocity final minus velocity initial. Okay. Now this ball is going downwards, and just before the change in momentum occurs just before when it bounces. Okay. So this is when it's going downwards, so it has a momentum, its velocity initial, and this is when it bounces off the floor. This is the floor. It bounces off the floor and it begins upwards again. This is its velocity final. Okay, so its velocity initial just before it hits the floor, and the velocity final just after it hits the floor. So there, just remove the whole. This is velocity final. Okay, so velocity initial. How do we get velocity initial and how do we get velocity final? Okay, we now know that for impulse, to get the impulse, it is just the mass times the velocity final minus the velocity initial. Okay. But we can already see something here. The velocity initial is going downwards, so it will have a negative sign. The velocity initial will have a negative sign, okay? Because it's pointing downwards. Due to our sign convention, it will have a negative sign. So this is our formula. Now let's calculate the velocities. Let's calculate velocity initial. How do we go about calculating the velocity initial? We've been given the height that this ball goes to. Okay, we've been given height. And so this is the velocity just before the impact, and the velocity initial is just velocity just before the impact. So it will be equal to the square root of 2 times the gravitational acceleration times h. You have seen this formula before. Okay, and if we plug in everything, 2 times 9,8, 1 times the height, 1,75 meters. That gives us an initial velocity just before it hits the ground of 5,86 meters per second. 5,86 meters per second. Always include your units. Now the velocity just after the rebound, this is V final. How do we get V final? V final is nothing but V2GH. So we use the same formula, 2 times 9,8, 1 meters per second squared, of course, and then 1.5. That gives us, let me see if there's still space. I'm looking at multiple screens. Okay. So I can't write it there. Let me just finish here at the bottom. That gives me an answer 5.42 meters per second. Okay, so that is the velocity at the final. So now we have the final velocity and we have the initial velocity. Okay, we have final velocity and initial velocity. Okay, so impulse, as we stated before, is equal to the mass times the final velocity minus the initial velocity. Okay, now we've already established that this velocity here will have a negative in front of it due to it being downwards, and we having chosen upwards as positive. So zero point 0.3 kilograms. I'm not writing units in here. The reason being I'm going to run out of space. So V final, what is V final? 5.42 minus, and then don't forget to put the minus in front of the initial velocity because the initial velocity is downwards just before the rebound, and that was 5,86 if I remember correctly. Close the bracket. And if we do the math, zero point 0.3 times that difference, actually you have to add these two now. That gives us, that's about 5.8, that's about 5, that's 10.4, 0.8, that's 11.2 or something. Zero point 0.3 of 11, so that's 3,33 something. In actual fact, it's 3,38, 3,38 kilogram meters per second. And remember, this is a vector, so it has a direction and it is in the j-hat direction. Since we chose upwards as positive, and since the sign here in front is positive, although we didn't write it, it means it has a upwards momentum, change in momentum, okay, a positive change in momentum. Now, B, estimate the contact time interval to be 0. Estimate the time the ball is in contact with the floor and use this estimate to calculate the average force the floor exerts on the ball. Okay, so remember this is correct, 3.3 kilograms. We got that answer correct. So B, we need to estimate the time the ball is in contact with the floor and use this estimate to calculate the average force the floor exerts on the ball. Okay, how do we get to calculate this? We need to estimate the time that this ball is in contact with the floor. Okay, so I'm going to take an estimate and say this is what I hate about this problem. They should have just told you. Okay, an estimate, my estimate for delta t, let's say 0.05. And the reason why I am guessing this particular number is the fact that I have seen the answers beforehand. I actually did this same problem last year, so I know it should be around here, 0.05. Now, to calculate the force, we know that impulse is equal to force times delta t. So it should then be impulse divided by delta t. Now we've already established or calculated the impulse is 3.38 kilogram meters per second divided by 0.05 seconds. And that, ladies and gentlemen, should give you an answer of 7 times 10 to the 2 or 700 newtons of average force. Okay, if you want to know what that is, how much force that is, take that value and divide it by 9,8 and you should be getting a mass, and that's the mass you need to hold up. That's the force required to hold that mass steady or moving at a constant speed. So the first problem, really easy, nice to get our jaws into and start off, wet our proverbial beaks. Okay, now the second problem is a bit more involved, a bit more strenuous on the brain, as they might say. 2. A car of mass m moving at a speed v1 collides and couples with the back of a truck of mass 2m moving initially in the same direction as the car at a lower same direction as the car but at a lower speed of v2. Okay, so we have a truck moving at a lower speed, the car's coming up behind it, collides with it, okay, and somehow this car, this bumper or something gets trapped in the truck or at the back of the truck and they start moving together as one unit. Okay, this is the collision part of this section. They are asking question 1, what is the speed VF of the two vehicles immediately after the collision? Okay, what's the speed of these vehicles immediately after the collision? Okay, First of all, we need to assume that this collision is inelastic. So the collision is inelastic. The collision, okay, let me just write this, inelastic collision. Elastic. This means momentum is conserved in elastic collision. Inelastic collision. So the momentum of the car, let me say the momentum of the car initially, or the momentum of the first vehicle initially plus the momentum of the second vehicle initially is equal to the momentum of the first vehicle initially plus the momentum of the second vehicle in finally. Okay, that should be finally, not initial. Okay, that just simply means that if you add up the collisions before and after the collision, it should be exactly the same. Okay, this is the mass of the M1. Okay, mass of M1. It is just M in this case, the mass of M, and it's moving at a velocity v1, they tell us, plus this one has a mass of 2m and is moving at a velocity v2, and that should be equal to the mass of this vehicle. Now they are coupled together, so they have the same, they will have the exact same velocity afterwards. So Vf will be the same for both. It is 2m. Vf is the same for both. Now we need to make Vf the subject of the formula. We can take out Vf. We are left with m, or m plus that is just 3m Vf. Okay? If you take Vf out, you're left with m plus 2m, which is just 3m Vf. If you cannot do that, the particular algebra there, please review your notes here. So we can take out m. You don't need to do that, but I'm just going to do it for a simple reason, which you will see now. It's v1. That is 2v2 over, okay, that is that. Now we want Vf alone, so we divide on both sides, and what we're left with is m v1 plus v2, or rather 2v2 over 3m, and the m's can cancel. Okay, so it will just be a third of v1 plus 2v2. It is just 1/3 v1 plus 2v2. That's it. So the answer Vf is equal to a third v1 plus 2v2. That's all. Question number 2, or B rather, what is it? 2 of the same problem. Question is, what is the change in the kinetic energy of the car truck system in the collision? What's the change in the kinetic energy? Okay, so the change in kinetic energy, you've done energy before, is Kf minus the kinetic energy at the end minus the kinetic energy in the beginning. Now the kinetic energy at the end is just a half times mass times the velocity at the end squared minus a half times m times the velocity initial squared. So the mass is now the mass of these two vehicles coupled at the end is 3m if I'm not mistaken. It is 3m, yes, because they're coupled together. And the velocity we just determined it to be a third v1 plus 2 v2, and then you cube or you square that. Okay, that is the kinetic energy at the end. Then you subtract the kinetic energy at the beginning, which is the sum of the kinetic energies of these two vehicles. It's just 2.5 m v1, its velocity to beginning squared, plus a half 2m, which is the velocity of the truck, the mass of the truck at the beginning, and its velocity at the beginning is v2. And then you square that to subtract it from that. Oh, you just see it's running out of space there. Uh, write it me. The initial mass of the truck is 2m. It travels with a velocity v2 initially, and you should square v2. Okay, and you close the bracket. Close the bracket. Okay, so now we have to just do simple algebra. Okay, you can then multiply all of that out. That is squared there. Multiply all of it out. This is an exercise in algebra, but eventually you will end up with negative m over 3 v initial v1 squared plus v2 squared minus 2v1 v2. Write it. If you do this math correctly, okay, which I did here, and it's going to take me a long time to write it down, but let me rather just do that so that I don't get asked where I got this and that. So if you square this, you will get you find its products. Here, you then subtract this from that. You should get m, which is common for all of them. You should get v1 squared over 6. I hope I did this correct. I did twice, so I'm sure. v1, v2 over 3. That is what you should get if you do the algebra correctly. v2 squared over 3 minus v1 v1 squared over 2 minus v2 squared. That's what you should get. Okay. Now, if you continue further on from that stop, you can freeze here. Okay. If you continue on and you simplify it further, your final answer will look like this. The change in the kinetic energy is m over 3 equal to v1 squared plus v2 squared minus 2 v1 v2. That is what the final answer looks like. Okay. If you do your algebra correctly, please keep track of your negatives and positives. For instance, this one here, I knew it had a minus in, it should have a minus in, but I struggled to find out where. I knew there was a negative change in the kinetic energy, so I knew that my answer should have a negative in front, but I struggled to find the negative. But eventually I did. It was just a simple sign error. Now, question number 3, having to do with blocks. Question number 3. Two blocks are free to slide along the frictionless wooden track shown in the figure. Okay, so I'll just show you what it looks like. It looks like this. This is block number 1. This is M1, and here is M2 here. Imagine this is a nice frictionless surface, and we have the height here up to here. That height is h. Okay, so this is the situation. So two blocks are free to slide along this frictionless wooden track shown in this figure. Okay, here's the figure M1, and the block of M1 is equal to 5 kilogram, equal to 5 kgs. Is released from the position shown at height 5 meters above the flat part of the track. Here, protruding from the front end is the north pole of a strong magnet, which repels the north pole of an identical magnet embedded in the back end of the block of mass M2. So M2 is 10 kgs initially at rest. The two blocks never touch. Calculate the maximum height to which M1 rises after this elastic collision. Okay, so it goes, they never touch due to the strong magnets. They bounce, M1 bounces back and goes back up the frictionless surface, and then they ask us how far does it rise upwards. Okay, so this is of course an calculate the maximum height to which M1 rises after the elastic collision. They ask us the mechanical, since this blocks is a frictionless surface, no energy is lost, so it's an elastic collision, meaning the mechanical energy at the beginning is equal to the mechanical energy at the end. Okay, that's simple enough. It's elastic. That's why they say frictionless surface. So the kinetic energy plus the potential energy initial is equal to the kinetic energy plus the potential energy final. Okay? Now, the kinetic energy initially is a half mv squared. It's the mass of one times the velocity of the first one. The potential energy so first we need to find this v1. Okay, the speed of m1. This is point B. Let's call this point B. We need to find v, the final speed at this point. v1, the speed of m1 at B. That's collision the collision, we are checking before the collision and after the collision. So the kinetic energy before the collision is a half mv1 m1 v1 just before the collision. But since it is at the same level, or it's at ground level, our reference, the potential energy is zero. Now, at the final, its potential energy is no longer zero, but its kinetic energy is zero since it flies backwards up the ramp, this frictionless surface, the track, but its potential energy is now m2. No, we're still just looking at m block 1. Sorry, block 1, and it has a height, and it is that height that we are after. So, what is its velocity initially? We can actually work that out. V1. Okay, we have its mass, we have the height that it goes from, okay, the height it moves from, h. H is, let me see, it's released from a position 5 meters, so h is 5 in this case. Okay, so we are watching this block as it bounces and then goes back after the collision. Okay, its final velocity before the collision and its potential height after the collision. So if we do this, okay, if we substitute in everything, we will get that V1 is equal to, V1 is going to equal to this M1 times G times 5 and divided by M times 2. So it will be this 2, and we've actually seen this formula before. It's just 2GH. We used it before previously, so we can work out V1. Okay, so we've used this formula just recently in our very first problem. So V1 is equal to just 2 times 9,8, 1 times 5. So we find the velocity just before the collision. It's 9,90 meters per second. That's the collision, just the velocity just before the collision. And now we need to find the speed of M1 just after the collision. Okay, so the speed of M1 just after the collision is going to be equal to the speed of 1 final. This is speed of 1 initial before the collision, and this one is after the collision. It is M1 minus M2 over M1 plus M2. Okay? That gives us a third, 1 over 3. That's 1 minus 1 minus 10, and then over 1 plus, 5 minus 10 over 15. So it's a third, negative a third, times 9 comma, and this is times Vf, times the initial velocity, that's the final velocity. So 9,8, 9,9, sorry, 0.90, that's Vf. So the final velocity should be negative, and it's negative 0.30 meters per second. Okay, that is the velocity just after the collision. Okay, now the speed of this block just after the collision. Now the speed this block, you want to know how high it goes after the collision. Okay, so we know that the potential height, it's H max. This is what we want. The potential energy, this should be G here, M1 G H max is equal to, the potential energy is going to be equal to its kinetic energy at that point. It's elastic. So M1 times V1F, the one that we just worked out. And if we make H max the subject of the formula, we have that it is V1F over 2G. So it is negative 3.30. Sorry, that is squared. That is kinetic energy. It's squared over 2 times 9,81. And that, ladies and gentlemen, gives us 0,556 meters. That's how high it will bounce back after this elastic collision. Very nice problem. And no questions. I see no questions. So everyone is with me. Okay, so let's continue. Problem 4. Here is some rotation about a fixed axis. It says a wheel starts from rest and rotates with a constant angular acceleration to reach an angular speed of 12 radians per second in 30 seconds. Okay. Find A, the magnitude of the angular acceleration of the wheel and the angle in radians through which it rotates in this interval. Okay. So we need to find the magnitude of the angular acceleration. So what is angular acceleration? It's equal to angular speed minus angular speed initially over time. The change in the angular speed over time, so that will be just 12 radians per second. And the time it takes in 3 seconds, so it is just 4, that's 3 seconds, 4 radians per second squared. That is the angular acceleration, is the change in the angular speed over time. That should just be final minus initial. So B, that is 1. Question number 2, what does it ask? The angle in radians through which it rotates in that interval. Okay, this is where you use this formula. The angle, it's the same as the distance, is the angular speed times time plus a half times the angular acceleration times time squared. Now we have the angular speed initially. We actually have everything. The angular speed, you say it starts from rest, so this is 0 plus a half times angular speed, that is angular acceleration, that is 4 radians per second, times, and it takes it in how many? 3 seconds. We square that, that is 4, that times 9. So a half of 4 is 2. 2 times 9 is 18, so that's 18 radians. 18 rad or 18 radians. Okay, that is a wonderful problem. Okay, final problem for today. Let me just check. It has some parts to it, various parts. Also on rotation about a fixed axis, this will be wheels. They are rotating about fixed axis. A wheel 2 meter in diameter lies in a vertical plane and rotates about its central axis with a constant angular acceleration of 4 radians per second squared. The wheel starts at rest at t0 and the radius vector of a certain point on the ROM makes an angle 57.3 with the horizontal at this time. At t2, find I, the angular speed. So I, so number one, we need to find the angular speed of the wheel, and for point P, at 2 seconds, find the angular speed of the wheel. Okay, so at 2 seconds, we find the angular speed. We have that angular speed, or let me just see, yeah, V final is equal to V initial, the initial speed, plus the angular acceleration times time. It starts from rest, so V initial is 0, plus the angular acceleration. In this case, they tell us it is 4 radians per second. And then 4, they find it, I want it after 2 seconds, so it is 8 radians per second. That's it. 2. Question 2. For point P, the tangential speed. Find the tangential speed at point P. Tangential speed means the linear speed at point P. So V is just R times the angular speed. So the radius, 1 meter, times angular speed, 8 radians per second, gives you a linear speed of 8 meters. That's all they mean by tangential speed. It's just the linear speed. So now problem or question 3, part 3 of this question. So far it's relatively easy. They ask us the total acceleration. The total acceleration. Okay. Let me see the best way to explain this. Okay, so the centripetal acceleration and deceleration after time t. At t equals 2 seconds. Okay, so the total acceleration will be equal to the acceleration, the square root, of course, since it's a square. It'll be the square root of the centripetal radial acceleration plus the radial acceleration plus AC, the radial acceleration as a t after 2 seconds squared. That is the total acceleration. Now, how do we get AR and how do we get AT? Now, AR, the radial acceleration, is just the radius multiplied by the centripetal, the speed, sorry, I keep wanting to say centripetal, the angular speed squared. That is the radial acceleration. So that is just the radius, which is 1 meters, multiplied by the speed is 8 radians per second, and that is squared, 8 radians per second, and that's squared. Okay, so that's 8 squared, that's 64, so this is 64 meters per second. That is the radial acceleration, and now we have the acceleration after, or rather AT is then equal to R times the acceleration, the angular acceleration. which is just 1 meter again, times the radial acceleration, or not the radial acceleration, I keep mixing this up, the angular acceleration, which in this case is 4 radians per second squared, and that gives me 4 meters per second. So these are both linear accelerations, AR and AT. Now to get A, which is the total, we need to find the square root of both of them. So it is 64 squared plus 4 squared, and the square root of that is 64.1 meter per second squared. That is the total acceleration, 64.1 meters per second squared. Okay. Finally, the angular position. Okay, that will be theta final is equal to theta initial plus angular speed times time plus a half times angular acceleration times time. I just plug in everything you know. That is just 1 radian theta initially, 1 radian plus you're gonna check something here. Angular position. Okay. Yes, that's 1 radian. Then we have a half times the angular is 4 radians per second squared, and times the time, which is in this case is just 2 seconds squared. But that's 4 times 4, that's 16, and a half of 16 is 8, plus 1, that's 9 radians, 9 rad, which is what the correct answer should be. Okay, that is all that we're going to do today, ladies and gentlemen. I hope you've kept up. I see no questions, so thank you for joining, and I hope you enjoyed the session. If not, please go through, or not much I can do if you did not enjoy it, but I hope you understood the session. Okay, thank you for listening, and I will see you all next week, Wednesday. Thank you.